Okay, holy cow. So, yikes. All right, so inspiratory pressure is going to go, or intrapulmonary pressure is going to go down during inspiration. What pressure is always negative helps keep the lungs inflated? That's intrapleural pressure, so PIP, and it's most negative during inspiration. Okay, and then transpulmonary pressure is the difference between the inside of your lungs and out into the pleural cavity. So if that equals 0, then you get atelectasis and lung collapse. Okay. And hang on, let me answer this email really quick, or this text really quick. Okay, and then this is known as a pneumothorax. Pneumothorax. Okay, so always remember air in the pleural cavity is a pneumothorax. All right. Okay, then we were talking about what other kinds of factors are going to affect ventilation. And so resistance and compliance are going to affect that as well. So in the bronchial constricts, what happens to resistance? It goes up, to airflow goes down. Okay, and then the two, oh, well, that was the end of my page. And then the two other important factors that play a role in, sorry, let me get rid of that. There we go. Clear. Okay, and then scroll down. This is annoying, but oh well. Two other important factors that play roles in ventilation, of course, is compliance and resistance. And so let me get this all, there we go. Now we've got a whole page on here. Okay, so histamine will constrict the bronchioles, increasing resistance, decreasing airflow, like in an asthma attack. Oh, if I have time at the end of the hour, I want to look at that article. Maybe I'll just wait until Monday to look at that article from the Atlantic that I want you to take a look at about COVID-19 and what happens to your respiratory system. Yeah, let me be a little more prepared. So we'll do that on Monday. Okay, epinephrine will dilate the bronchioles and decrease resistance and increase airflow. And acetylcholine, because, so remember, epinephrine is part of sympathetic nervous system, so we know that's what sympathetic stimulation is going to do. As far as bronchial diameter is concerned, it'll also increase your breathing rate and depth, but within the lungs, what's going on. Acetylcholine will constrict the bronchioles, increasing resistance, decreasing airflow. So fibrosis, which I'm interested to see, will we get people who recover from COVID-19 if they're going to have some fibrosis? Will they get some scarring? And will we get, bunches of people, even though they've recovered, will they have chronic respiratory problems after this? And then how will they do in just a normal, red flag day where there's so much pollution in the air that they can't go outside? So who knows? Don't have any idea, but those are, some things that we need to think about within the medical field. What are our long-term ramifications of this disease? Fibrosis will decrease compliance, making it harder. So harder to inflate the lungs. Okay, and a decrease in surfactant. Remember, surfactant makes the alveoli, there we go, or the lungs more compliant, easier to inflate. And so a decrease in surfactant will decrease your compliance. It'll make it harder to inhale. They won't be able to inflate very well. Okay, so with gas exchange, remember CO2, you do not have to have the same pressure, partial pressure, as you do oxygen in order to get CO2 to diffuse into the plasma, and that's because of Henry's law. So Dalton's law of partial pressure is, just that whatever concentration of a particular gas that you have in a mixture, whatever pressure that gas exerts, the percentage of that individual gas within the mixture will be the same percentage of the pressure that is exerted. And here's another thing, you know, this is, I just always look at it and go, wow, this just isn't by accident. You know, even with global warming, we still have very little CO2 in the atmosphere. And so if we're breathing in very little CO2, you better hope that CO2 is really soluble so that it gets into our plasma from our tissues and then carried out from our lungs. And so, I mean, just there's so many little things where you go, holy cow, if that didn't happen just like that, it wouldn't work. So I just love it. I swear, respiratory system works better than anything else for me like that, I think. Okay, number 2, efficient external respiration depends on 3 factors. So this, why does the O2 go into the blood from the alveoli, or the CO2 from, well, yeah, the O2 from the alveoli? So of course our partial pressure, so our PO2. And then the respiratory membrane, and we'll go through, respiratory membrane. Thickness and surface area, so, you know, as big as a tennis court, and then ventilation and perfusion. And then, of course, we'll go over that again. And then we didn't worry about that. Okay, so this question number 4 deals with ventilation and perfusion idea. So remember, picture the little shriveled up alveoli, not getting a lot of flow into them. So PO2 will be low, PCO2 will be high, the arterioles will vasoconstrict, the bronchioles will bronchodilate. So remember that O2 is over vascular smooth muscle, okay, VSM, and then CO2 controls bronchial smooth muscle. Okay, and then airflow if it's increased, and so now we've got good ventilation, so we also want good perfusion, so we're going to vasodilate, and then we don't want the air to leave as much, and so then when we go to the next page, then we're going to bronchoconstrict. Okay, so let me clear my drawings on that, and then, oops, go to the next page. Okay, and let me write again. Okay, so we're going to bronchoconstrict. All right, and then our internal respiration depends on 3 factors. So this is exchange at the tissue level. So external is in your lungs, internal respiration is at the tissues. So then again, our partial pressure, PO2, and PCO2, of course. And then, but we're really talking about PO2. And then the temperature, nope, that's pH, the acidity of your tissues, and then the temperature. And then we're going to talk more about that in a few minutes. Okay, those factors that govern loading and unloading of O2 and CO2. All right, gas transport. Remember that 98.5% is bound to hemoglobin, which means there's a 1.5% left in the plasma, and we need to have at least some gas in the plasma, or else it's not going to flow. Okay, hemoglobin is composed of 4 polypeptide chains and 4 heme groups. Oxygen binds to the iron. Okay. Josh just asked, was this the last lecture we did before spring break? I'm just putting everything all together. We did more than this. So we got some other material on the next page. No, what did we, yeah. So we finished off like, because we played all the little games on the little practice question thingies. And so I think that was the last thing we did before spring break. But we've completed now, after Wednesday's lecture, we're through with respiration. That's why today is kind of just wrap it all up and put it all together in a package. Okay, let's see. so binds to the iron. I hope that answers your question, Josh. After one molecule of O2 binds to hemoglobin, then we have cooperative binding. So it makes it easier for the other molecules to bind, the other oxygen molecules to bind. So oxygen on hemoglobin is oxyhemoglobin, HbO2. And when oxygen is unloaded from the hemoglobin, then it's deoxyhemoglobin, but remember it's going to be a buffer. Oops. It's going to become a buffer and bind to that hydrogen ion that's given off when CO2 is unloaded. Nope. When CO2 is loaded. There we go. Is that right? Yeah, when CO2 is coming in from the plasma. Okay, let's see. Because always think when oxygen is loaded, CO2 is unloaded. When oxygen is unloaded, CO2 is loaded. Okay. Oh yeah, because we're going to the right. Oh my gosh, you guys. Okay. Let's see. So we have 104 and basically 100% saturated, but it's really 98 when we look at it on a pulse ox, but that's okay. 100% saturated, and then 40, but this is what we really want to remember, and this is 75% saturated. So remember, out of a hemoglobin molecule, 1 oxygen is going to pop off. Now, remember with the oxygen hemoglobin saturation curve, looks like this. So here we are at 100, and we're at 100. And if we go to 80, we're still pretty saturated. So will the saturation decrease significantly? No, it won't. Okay. And then the effect of exercise on tissue PO2, of course, it's going to lower tissue PO2. Okay. And so then what does that do? Okay, so I have to clear this page. I don't like that I have to go through all of this to go to the next page, but whatever. Okay, so since our PO2 went down, and our PO2 goes down to about, there we go, 20, then will hemoglobin saturation decrease significantly? Yes. Okay, because it's going to go to about, 35% saturation. Okay, so we've got a 40% decrease in overall saturation from 75 to 35. And so how does this help the tissues? It releases more oxygen. And who needs that oxygen? Well, our tissues need that oxygen. Releases more where it's needed. Okay, now name the other factors that alter PO2. So remember, besides just a change in the partial pressure of oxygen, pH and temperature and PCO2. All right, so now during exercise, what's going to happen to these factors? Okay, so so let's just do PO2. Whoops. Okay, so PO2 goes down and PCO2 goes up and pH goes down and temp goes up. Okay, so this is in the tissues. So if we go over here and we tell what's going to happen in the lungs, then it's going to be the opposite. So in the lungs, I have an increase. So this is unloading and PO2, and a decrease in PCO2. And always remember these, an increase in pH, because next week is April, friends, and we'll be starting into On Wednesday the 8th, we will be starting, no, we won't, because we'll be doing urinary system, and then we'll do acids and bases. But it's April, we're finally there. And then what's this one? Temp. Okay, and so all of these characteristics are going to facilitate O2 loading. Okay, and then the factors, so these factors right here, to make it easier to unload, shift the curve to the right. So there's not as steep a curve. So I'll do it over here. So our curve used to look like this. Ooh, that's really steep. But now it's gonna flatten out more. So this would be lungs, this would be tissues, if we wanted to look at the difference between the curves. Okay, so any questions on any of that O2 stuff? Okay, then we'll move on. If you still have a question anytime, just go ahead and type in. Okay, so dissolved in plasma, 7 to 10% combined with hemoglobin. If we're gonna do 7, then we do 23, but if we do 10%, then we would do 20. And then, but this is the main number, this one right here. 70% is converted to bicarbonate ions. When CO2 binds to hemoglobin, remember it's carbaminohemoglobin, and it's gonna bind whatever to, okay, so here would be my heme in the middle, CO2 would bind somewhere else. So not to the heme molecule right there. Okay, so you know what? I am gonna type out our equation. CO2, whoops, plus H2O equals, sorry, but pretend it's got arrows on it, H2CO3, and then H plus and plus, whoops, plus HCO, whoops, yeah, 3 minus. Okay, so CO2 combines with water to form carbaminohemoglobin. No, it doesn't. What am I saying? I just read that one. To form carbonic acid, so that thing right there. The catalyst for this reaction is carbonic anhydrase. Oops. Okay. The acid then dissociates into hydrogen ions. So let's draw again. Whoops. Hydrogen ions. And bicarb. Okay, when bicarbonate moves out of the cell, chloride ions move in, known as the chloride shift. Okay, and then the reaction occurs in the opposite direction of the lung, so CO2 can be released. Okay, so remember we're going to go to the right in the tissues. And please memorize this equation, or this reaction right here. I guess it's an equation. And then left in the lungs. And if you want to take it one step further, if you hypoventilate, so I'm not breathing, like if I have COPD, emphysema, chronic bronchitis, COVID-19, unfortunately, I'm going to become acidic. So hyperventilate, hypoventilate. Yes, HCO3, no, Joanna, HCO3 is bicarbonate. This is carbonic acid. Okay, and then HCO3, this is bicarbonate ion. Okay. So all the people that are suffering from severe COVID-19 are also in severe respiratory acidosis. Josh, just because you know what that is. And then, so how do we treat them? Well, lots of things. Their kidneys are going crazy trying to reduce the acidity of their tissues, but we want them to hyperventilate, but they can't because they're all filled up with fluid. And so that's why they have to be on a ventilator. And well, among other reasons why they have to be on a ventilator, and why people are, you know, like New York is crazy bad right now. There's no ventilators, there's nothing. And I read an article a couple days ago, 13 people died in Queens. Oh, let's see, Trevor, the CO2 binds with water to form carbonic acid. So this right here, carbonic acid. Yeah, carbonic acid, H2CO3. That's why I just wrote out the whole equation, because all the answers are right there. Oh, and so then if you're hyperventilating, then you'll be pushing the reaction to the left and raising your pH. And so if I have acidosis for some reason, I'm starving or I'm a diabetic or something, then you'll notice that they will hyperventilate to try to reduce their pH. No, yeah, reduce their pH. Raise their pH, reduce their hydrogen ion concentration. Okay, anyway, that was beyond, that's for 2 weeks from now, or 3 weeks from now. Okay, so a decrease in hemoglobin O2, CO2 loading, or O2 loading facilitates CO2 unloading. Either way, when we're talking about carbon dioxide, is Haldane effect. I don't know if any of you took an opportunity to read about Mr. Haldane. Oh my gosh. So you might want to while you're on a break and don't have something to do. So read about Haldane and his deep sea diving adventures. Okay. And then we got just this last little bit. So a decrease in CO2 loading facilitates O2 unloading. I can't get my little, there we go. Okay, so O2 unloading from the tissues, and this is the Bohr effect. And what I like to remember with Bohr effect is always decreasing pH, because that's really what's driving it. And as the pH drops, as we get a whole bunch of hydrogen ions, then they're going to compete for hemoglobin. So the O2 will pop off, and the hemoglobin will, I mean, the hydrogen ion will come in and get picked up by the hemoglobin. So, okay. So I think we're probably good on the rest of our packet, because we just did this recently. And let me know if you don't have any, if you're missing some answers. What I think I'll do is post a filled out one of these in the announcements, and then in case you don't have one. So, okay, so we're gonna go ahead and get rid of this. Clear and get rid of that, and then we're gonna go to my PowerPoint. No, hang on, let me get rid of that. Click on my PowerPoint. Okay. Uh-oh, running out of time. This meeting will end in 10 minutes. Okay, so here's what we may have to do is stop it and then start a new one. So it's not that big a deal, like what we did on Wednesday. I thought it would be nice and give us all the time that we want, but apparently not. Freaking stupid thing. Okay. But it's all good. We'll make it work. Okay, so let me go back, share my screen. I'll just keep track of time-wise. Okay, so you should be able to see my PowerPoint, and as soon as it goes into PowerPoint form. All right, so here we go. Okay, so what I want to do is go through the objectives and see what we've accomplished, and then what kinds of things we need to go back and touch on again before we're done with respiratory system. Okay, so distinguish between conducting and respiratory zone structures. So remember, conducting zone structures are going to be those that just take the gas. Well, we'll just go to the next slide. Okay, so deliver gases to and from the respiratory zone, upper respiratory tract. So all your nasal cavity and the pharynx. So the 3 parts of the pharynx, the trachea and the bronchial tree, up to and including the terminal bronchioles, down to the end. And then remember, what is the point of the conducting zone structures in addition to delivering the air to and from the alveoli, is to warm and moisten and filter the air as well. Okay, remember respiratory zone structures then you know what, I don't want to keep flipping back. We're just going to go down through the notes. Okay, so everything in this picture is a conducting zone structure. Okay, then we have respiratory zone structures where the gas exchange occurs. So remember that because they are respiratory zone structures, that, I'm just going to put a little note in here, like when I usually write on the board. They are surrounded by alveoli. Okay. No, they're not. I'm sorry. That's dumb. They are not surrounded by alveoli. They are surrounded by capillaries. Oh, booey. Oh my gosh. Okay, and why do they need to be surrounded by capillaries for that gas exchange to occur? So everything in the respiratory zone has capillaries on it, surrounding it. Okay, so bronchioles, respiratory bronchioles, alveolar ducts, and alveoli. So if we go to the next picture, oops. Then here we can see, so everything in this picture, that, I don't like how they went up so far. It should be way, 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 because we branch about, there's about 23 levels of branching that we get in the respiratory system. So long, 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 long branching. Okay, so here we go, respiratory bronchioles, and then the alveolar duct. Okay, and then the alveolar sac would be, here would be a sac, here would be a sac, but then the individual little grape-like alveoli. Now remember, in addition to the alveoli, that, you know, just this little thing we want to remember, what else about alveoli? Here in this picture, we can see those 5 rubber bands. So the elastic tissue that's covering each alveolus is going to allow the compliance. Sorry, I'm thinking too much about time. I'm not going to think about time anymore. I'm trying to figure out what to do about that. So this is what causes the alveoli to be small so that we can create that negative pressure inside the pleural cavity, but then it's also going to allow the alveoli to go back to their original diameter when after we've inspired. Remember, we need to increase the pressure, and so if the alveoli did not have these elastic fibers around them, then they wouldn't recoil and we would never get the air back out. Well, guess what? That's what emphysema is. And so because the person has overinflated their lungs because there's so much gunk inside of their lungs from smoking or other kinds of respiratory issues, that all these elastic fibers got broken, and so now you've got overinflated alveoli that won't shrink back up again, won't recoil, and we can't get the air back out. And so then the air remains trapped, and there's no O2 in it anymore because we're not exchanging with fresh air, and your respiratory or your residual volume goes up, and it's bad all the way around. Okay, so that's the respiratory zone structures. Here shows how everything is all lovely and vascularized. This is a real good diagram of showing the respiratory membrane. So remember, you have the simple squamous epithelium, or that type 1 alveolar cell that forms the wall of the alveolus, and then you're going to have the fused basement membrane right here between, and then you're going to have the simple squamous epithelial cell of the capillary. And so the O2 just has to pass through 1, 2, 3, 4, 5 places, and then 6 if you're going with this cell membrane to get into different things that has to pass through to get into the red blood cell, and then out the other way. So we want our respiratory membrane to be very, very thin, but very expansive. We want lots of surface area for our exchange to take place. While we're still in this picture, here are the type 2 alveolar cells, the green ones. These are the ones that produce surfactant that reduces the surface tension of the alveolar fluid that's secreted by the type 1 alveolar cells. And then these little blue jobbies, those are my favorites. They're the macrophages, the resident alveolar macrophages that hang out there and hopefully defend against you know, coronavirus. But here's the problem, is that they're not particularly good at virus infected cells. What we need is a you know, some cytotoxic T cells that are down in here. And but then that presents a whole lot of other problems that we'll talk about once I put things together for you about COVID-19. Okay, so moving on, we know all of this, we know that, we know, okay, so remember PALV is the pressure inside the lungs, specifically within the alveoli, and that's what we're trying to change as we're ventilating in and out. So here just shows the numbers. So atmospheric pressure when we're not breathing, then intrapulmonary pressure, this should say ALV with the way that we do it, would be 0. And then here is that negative partial pressure, or not partial pressure, but that negative intrapleural pressure that we find in the pleural cavity. And then transpulmonary pressure is the difference across from what's inside of the alveoli to what's outside here. And it should always be negative. Transpulmonary pressure always needs to be less than 0 so that the lungs can always expand. Okay, so we got that. And then here's just what happens. So here's what's happening, intrapulmonary pressure. Here is intrapleural pressure. This is little, see how it's not a nice smooth, it's like shoots back up there fast. This is hysteresis. And what that is the scrunching up of the elastic fibers. So it goes out a lot faster than what it came in. Okay, so when we're expanding, it expands slower than when the lungs contract because of that elastic stuff. And so anyway, that's just what that is. And then here is just our volume of breath that's moving during respiration. Okay. Okay, so how do we establish an intrapleural pressure? Those were the 3 things that we wrote on the very first page by what pressure is always negative, helps to keep the lungs inflated. Okay, so we have, the lungs have tendency to recoil due to elastic fibers around the alveoli and occupy the smallest spot possible. The lungs also contain alveolar fluid, tends to pull the alveolar walls together because of surface tension. And then the elasticity of the thoracic wall, which is on this last one, let's see, no. And then, it said it on our packet, but I didn't put it in here. Okay, so what I'm gonna do right now is stop recording and then gonna start a new one because I'm